Okay, so proceeding along. So again, we've spent a bunch of time talking about Chapter 15, various different of these accumulation theorems, boundary theorems, density theorems, whatever you want to call them, all these kinds of theorems that all have all these kind of common features. And I gave y'all a sort of, strategic outline of how to go about using those theorems to compute line integrals and surface integrals. Step-by-step process. It relies heavily on the diagram, right? Now, this is the R3 diagram. There's also an R2 diagram. But there's sort of more interesting stuff going on in the R3 diagram, so I want to focus on this. And so anyway, we went through that process last time. I won't repeat it, but we also did a couple of examples, and I just want to finish up our last few examples here. So here we go. Want to compute a flux? Oh gosh, not again. Okay. So again, my computer. There's something weird about when I opened that thing before I plugged into the screen there. Sorry about that. Okay. Okay, here we go. Here we were. So here's a line integral, right? We want to compute. The vector field is given. The curve is given, and let's compute that line integral. Okay. So first of all, let's think about our options. Now, obviously, there's the brute force option, sort of always on the table, right? You can just plug and chug. So, well, let's consider some other options. Let's see here. Let's look at our vector field. By the way, reminder, one of our first things to do is, let's go back to the diagram. First thing to do is identify where we are on, this one too. I have a separate instance of this thing. Oh, sorry. Man. I haven't gotten burned on this for quite a while this semester, so I guess I got cocky. Bear with me just a moment. Go down to where we have this diagram somewhere. There we go. We'll use this one. Okay, so here we are in the R3 diagram. We're asked to compute a line integral. That means that we're given a field and a curve, right? What does the diagram tell us to do? It tells us to compute the curl of that vector field. So let's do it. The usual process. Y partial of x minus z partial of z. Okay, so that gives us a minus 1. The next component is z partial of y minus x partial of x. That gives us minus 1. Keep going. Our curl is this. Okay, now, immediate conclusion. The curl is not 0. Therefore, I know that there is no anti-gradient. So don't look for it. Right? It's not there. It's a wild goose chase. So the fundamental theorem of line integrals is off the table. You could not possibly use this because there is no anti-gradient. Everybody on board? Okay. All right. So because of computing the curl. All right. Now, next thing, is there an anti-boundary? Is this curve the boundary of some surface as pertains to the question of can I use Stokes's curl theorem? Okay, well, let's look at this curve. We got to think about the curve in detail. So we're looking at where this plane intersects that cylinder, and I'm not going to draw a perfect picture of it because, well, it's hard, right? But we've got a plane intersecting a cylinder, and I appeal to your geometric intuition. That makes an angled ellipse. Right, so there's our curve. Oh, wait a second. Now, oriented counterclockwise as seen from above. Right, so the orientation has to be given if you wanted to compute a line integral. So counterclockwise as seen from above, and so that means like this. Yeah, everybody good there? Okay. All right. So, is this curve now, going back to, here's our question, can we use Stokes's curl theorem To decide whether we can use Stokes' curl theorem, I need to know, is there a surface whose boundary is that curve? And the answer to that question is yes. Right? So here it is. I can use that surface. Or, depending on how weird I feel, I can use that surface. Right? But, of course, we're self-interested. And so we're going to pick the easiest surface we can think of. I propose that one. Okay. So let's call this surface S. And Stokes' curl theorem then tells me I can look at a flux through S of the curl, which I know, dot ds. So there's an alternative. Now, I'm going to let you all crank through the details on that. What I'd like to talk about here is, was this a win? Did this help us? And I think it's a close call, to be totally honest. I'm not 100% clear that this is a win. Let's look for a moment at what our alternative would have been. Let's see here. Let me move this thing out of my way. Our alternative, the plug and chug method, would have had us computing integral over this curve. We've got an easy vector field, y, z, x, dot x prime dt, and x is easy to parameterize. This curve, no big deal. Right? We're looking at this cylinder means we're looking at points that are sitting over the unit circle, so that means the x and y coordinates, they're just going around in the usual circle, cosine t, sine t. It's really easy to parameterize x and y. And then z, how do I get z? Well, according to this, z is negative x minus y. Right? So negative cosine t minus sine t. And if you take this parameterization here and plug it into there, it's not that bad. Right? I mean, not clear. I'm not saying that's the way to do it, but that's certainly a reasonable option. Again, the alternative here, using Stokes' curl theorem, well, the curl is constant, and that's nice, but I do have to parameterize that surface. Not that that's particularly bad, right? This surface, again, it's easy to write this with the graph parameterization, right? Z is a function of x and y on this surface. I wanted that in orange, sorry. Hang on. On this surface, z is equal to negative x minus y. So the graph parameterization is pretty straightforward. For that surface. But then you have to write down xu and xv and take the cross product and, go through that whole process. I am not entirely clear which one of these is better or worse. I don't know. I guess I'd lean toward the Stokes' theorem option, right? But anyway, the point I'm trying to make here is don't just always assume that, automatically because you invoke one of these big theorems that whatever new integral that you turn it into is going to be, an order of magnitude easier than the original question. It's not necessarily, right? So this is always a heads up, think about your options kind of a situation. So anyway, I think it's a sort of an interesting comparison here, yeah.
Instead of doing xu, xv, did you draw the normal vectors on the portion of the plane?
That's a tricky matter. So you can find the unit normal vector, right? The problem is we're eventually going to need to know this ds if we want to do this integral. And so now you could say, well, I know the unit vector, and side note, the unit vector is constant. It's convenient, right? The problem is then I would have to compute the area of that tilted ellipse, right? And that's a little tricky. On the other hand, if you want to know, can I just look and find capital N? Definitely not. Capital N depends on the parameterization, and I do see this a lot. So I'm glad you asked that question. Lots of students mistakenly write as follows. They say, okay, well, I have, let's see here. The curl is -1, -1, -1, and the normal vector is, let's see, what was it, 1, 1, 1. And students will just write this down. By the way, let me get rid of all this. I don't want to look at that anymore. A lot of students will just write down that the normal vector is 1, 1, 1. That's wrong. How do you know it's 1? Why isn't it 2, 2, 2 or 7, 7, 7? Right? I mean, the fact that we happen to coincidentally, for no good reason, write down the equation as 1x plus 1y plus 1z doesn't really mean anything, right? So this normal vector has a meaningless magnitude in this context, but we need the magnitude. We need to know what that magnitude is, because that's the depending on how you look at it, the scalar stretching factor, or whatever. Yeah.
Well, couldn't you just use the unit normal?
You can use the unit normal, but that's right. And if you do that, if you then say, all right, I'm going to say, divided by the square root of 3, then your differential over here is ds. And all of these constants factor out, sure. Right, all of this goes out, and you have whatever that constant ends up being, and then double integral over s of ds, and there's that area of the tilted ellipse problem. That, it's like, well, I mean, yeah, you can do that, right? But it's not quite barnyard variety, because at a minimum, if you wanted to, take the high school geometry approach, you'd have to figure out what the two different radii are. You'd have to be entirely clear on where those... I mean, it's a hard geometry problem, right? In fact, the easiest way to do this, I think, would be to parameterize and do an integral, right? So I think it's ultimately sort of self-defeating. Yeah, it technically works, but it's not a silver bullet, right? Okay. All right. Now here's a variation on that question. Same vector field, very similar looking surface. You notice, plane, cylinder. It almost looks like the same problem. Here, something pretty significantly different does happen, and that is, even though it's the same cylinder. Right, it's a different plane, but when I draw these things, it's not like I'm drawing them, to scale. So still an ellipse, right? Still oriented like this. But now being a different question.
Well, this is sort of like a general question, but related to the previous one.
Okay.
So when can you just say that, when can you just recognize, the unit normal vector?
Yeah, so, if you recognize the unit normal vector, then you're going to find yourself left with this, right? Or even worse, possibly an integral, of a non-constant inside of there. And so the point is, in this best case scenario, you have to be able to determine the area of the thing that you're looking at. So now if you already know the area, right, if it really is truly barnyard variety geometric figure, then yeah, cool, go ahead. By all means, that's super. And that's one of these sort of really, geometric good fortune things that we've talked about a bunch. It's just that that's not the case here. That's the only catch. Yeah. Right. Okay, so here, this question. This is actually another answer to your question. We'll see when we get there in a moment. So, same curl, Stokes' theorem, blah, blah, right? So here's our surface. And I'm going to rewrite the integral then as, let's see here. Pencil. Equals surface integral curl dot ds. And here I am going to write it as in ds scalar. And so what's the benefit of doing that here? I still don't know what the area is, right? But in this case, we get a different kind of geometric good fortune, and that is this dot product is evidently 0. Let's just remember what the arithmetic is here, right? So what we've got here is the curl was -1, -1, -1. The unit normal vector now I can read straight off of here as 1, 0, -1 divided by the square root of 2. And so even though I don't know that, I do know that is 0, and therefore don't care. Every so often you get lucky, so, be on the lookout for that kind of thing as well. Everybody happy? Okay. All right. Oh, hey, by the way, let's talk about orientations. What's the orientation on this? So I did kind of blow that off over here. What is the orientation on this You know what? I may have a cleaner picture. Yeah, I have a better picture here. Let's talk about. Okay, what is the orientation here? Is it upward or is it downward? And again, the answer to this question, the relationship between a boundary orientation, a boundary curve orientation, and its, and the associated surface orientation, it's always this thing, right? So thumb is your surface orientation. Fingers of your right hand are indicative of the swirl that tells you the boundary curve orientation. So you just got to play this game twice, and which way do you have to orient your thumb to get the swirl to go the correct way? And that's upward, not downward. Yeah.
Just to clarify, say it was clockwise, would you put the negative sign outside the double integral, or would you apply it to what changes signs within the vector?
There's different ways you can go about that. What I would probably do is not put a minus sign anywhere, but just make an appropriate minus sign in the normal vector itself.
Okay.
But suit yourself, right? What you really care about is whether the normal vector you've written down is either the correct normal vector or the not correct normal vector, right? And by the way, it looks like I blew it here. Let's take a moment to recognize that in my carelessness, right? And so good that we see this little bee sting before the final, right? Even though the answer is 0, right? I would still lose a point on this, at least, okay? Because I wrote down as a normal vector a vector which is wrong, right? I wrote this thing, which is pointing down-ish. I accidentally wrote down that. Everybody see what I did wrong there? No, I was just being careless, right? But it's definitely something you want to pay attention to. Yeah.
For the one above it, like when we looked at the kind of brute force way,
Yeah.
for that method, you don't really have to look at the orientation?
In effect you do. It just appears in a different way. You have to parameterize the curve the correct way, right? So the curve was given as oriented counterclockwise as seen from above, and that means sort of like this. Right, so you have to make sure that when you parameterize, you're thinking about the x and the y and the cosine sine, right? I just wrote down cosine sine, but I was aware of the fact that cosine sine is going like this, and that makes my ellipse oriented like this, and that is, counterclockwise as seen from above. Yeah. Right. Yes.
So if you're parameterizing a surface, and you want to follow the same, like if you're doing a line integral.
Yeah.
So based on the
parameterizing a surface, it's actually really hard to sort of see it coming in advance when you parameterize. I guess I don't have it on the page anymore. But when you're parameterizing a surface, it's really hard to see which way you're going. One little quick hint: if you use the graph parameterization, where z is a function of x and y, and if you use the graph parameterization exactly the way we've always done it here, it'll always parameterize up. Neato. Right? So good fact to, sort of keep in mind. But other than that, if you parameterize by some other method, you got to check. It's hard to see. It's really hard to see it coming. Yeah. Okay. Okay, here's another example. Here, now we're moving on to computing fluxes. Here we're okay, let's go to the diagram. Here's our R3 diagram. We've been asked to compute a flux. That means that the vector field I'm given, I'm going to need to compute the divergence of it. Right? Okay. Who can, this is a pretty easy one. You can compute this divergence in two really easy ways. One really easy way to compute this divergence is just do the partial derivatives. They're super quick, right? And the divergence is 0. Yeah? Everybody on board? Okay. Here's another way to compute this divergence. Super quick. We are told elsewhere in the problem that this is a curl. And therefore its divergence is 0. Yeah? Ready good? So it's a good thing to be heads up about. Alright, so we're given a surface, we're asked to compute a flux. Let's think about our options, going back to the diagram. We did get 0, so that means that there is an anti-curl. Not that we know how to compute anti-curls, but I suppose Stokes' curl theorem is still on the table. Hey, wait a second. I don't know how to compute anti-curls, but we should know how to recognize when they are given to us for free, right? So There it is. That's the anti-curl. That is the field whose curl is F. Right? That's literally what this says. Right? So heads up for that. Sometimes it's given like this. Right? Another way that I suppose it could be sort of encoded would be if I have a question, something about current and magnetic fields. Well, don't forget, right, that the curl of the magnetic field is the current field, and so there's a free anti-curl that can be interpreted in there. Right? So heads up on that as well. So anyway. So we're computing this flux. Back to our diagram. We can find that. So Stokes' curl theorem is a very reasonable option here. Okay. Now, on the other hand, let's look at our other option, our surface here. We're looking at the part of that. That's an upside-down paraboloid, an elliptical paraboloid. We're looking at the part above. We're looking at the part above the XY plane. Right, so our surface is something kind of like that. It's not a boundary. Again, be super careful about the phrasing. There's this natural instinct for students to want to look at this and say, "Oh, yeah, well," and you got to include that. No. Nowhere on here does it say that. Right? So you interpret literally. This right here says paraboloid. The surface is part of this paraboloid. Specifically, not only does it have to be part of the paraboloid, it also has to have a non-negative z coordinate, right? But that doesn't say, and furthermore, glue to the bottom this part of this plane that's the boundary of z greater than or equal to 0. Right? There's a bunch of words that are not there. Everybody okay with that? Right, so you just got to be really, really careful. This kind of detail matters dramatically. Right? Yes.
How would that probably be conveyed? The boundary.
Oh yeah. I mean, I'd have to. I could say the boundary of the solid. Like if I said here's the solid given by like if I made this an inequality. Let's look at all the points that are below the paraboloid, and then say intersect. Z, above the plane. And then I said, look at the boundary of that solid. But I would have to say boundary, right? Or I could explicitly say this, comma, and then, and also attach, and then explicitly describe that bottom surface. Yeah. Right. So, yeah. Okay. So, our surface. Not a boundary. There is no solid region whose boundary is our surface. Doesn't exist. So Gauss's divergence theorem, off the table. Everybody on board? And it, again, always sad, but there will be, hopefully not in this section, right? But somewhere in Math 212, someone's going to answer this question by saying, "Oh, flux equals triple integral divergence." dv equals triple integral 0 equals 0 box smiley face, right? So we're going to get those, and there's nothing that's been written down here that is both true and relevant to this question. The divergence is 0. Okay, so this is 2 out of 20. Right? So please, I'm begging you, please don't do this. Right? Right? It's tragedy when this happens. Okay. All right. Okay, so we looked at our two accumulation theorems, boundary theorems, whatever you want to call it. We have one functional candidate, Stokes' curl theorem, and so you can rewrite this as a line integral. And off you go. And let's just do that real quick. Let's see here. So this is equal to a line integral over that boundary curve. Let me say boundary S. Of the anti-curl being 0, 0, x, y, z, right, dot dx. Now, unfortunately, at this point, what we have to do, let's look again at our deal. Here's our surface. Right, there's our oriented up. Right, so there's our surface. That means, again, right-hand rule, play the game. Our boundary curve down here, that curve is oriented this way. Right? And now I got to parameterize that thing. I mean, it's a little bit of work there. Anyway, it's not the worst thing in the world. By the way, this is one good observation you can make right away is that all of this curve is in the plane z equals 0. So our parameterization is going to be x, y, 0. And therefore, dz is equal to 0. And therefore, in this dot product here, you're going to get 0. Everybody see what happened there? So that's nice. Saves you a little bit. Anybody have any other ideas for this? Another option? Yeah.
You could do like the flux through the circle on the bottom.
Yeah. So keyword, surface independence. That's right. You're absolutely right. So surface independence is another option. So remember, this is given as a curl, and therefore the divergence is 0. Divergence 0 means that this is surface independent. That means that I can, while Stokes' theorem works just fine, right? Very nicely, in fact. Another very reasonable option is just to say, I don't like that surface. I'm going to use this surface down at the bottom, and let's get rid of that guy. I don't need him anymore. And let's just compute that flux instead. And again, something really nice happens. Fortunate coincidence. Our normal vector there is really easy to write down, right? And so then f dot in turns into 0. So that's flux. Super easy to compute. So this problem is a wonderful application of Stokes' theorem, and it's a wonderful application of surface independence. Yeah, everybody good? All right. Okay, so we are getting shorter and shorter on time. So let me blow through this last example very quickly. Being asked to compute a flux. So we're looking at a flux, compute the divergence. It's not 0, so Stokes' curl theorem is off the table. Right? On the other hand, let's look at our surface. Our surface, unit sphere oriented outward, that is a boundary of a solid. Right? So there is an anti-boundary. Gauss's divergence theorem does apply. You could just compute a triple integral of divergence over that solid. The solid is pretty easy to deal with. What we have here, triple integral. Oh, that's harsh. Triple integral over the ball of the divergence. The divergence, by the way, if I remember correctly, is 1. Right? So we just end up with the volume of the ball. How we doing? Yes?
How do you know the orientation of a solid?
Yeah, well, so solids, I mean, the way we're going to do it in Math 212, we don't really have orientations on solids. There is. You can do that, and it makes sense. I just don't want it's a digression I don't want to get into. The point is that if you have a solid, then the boundary surface, that word boundary, implies an orientation on the surface. And so if you want to relate a surface to a boundary of something, you just have to pay attention if that surface's orientation is the same as the unavoidably outward boundary orientation. And if those are the same as they are here, then you're good. Right? If they're opposite, then you just say, well, I'm not going to compute. Like here, let me say, if this were inward. Right? If it was oriented inward, then I would say, okay, well, my surface, that flux is the negative of the boundary flux that I can compute with Gauss's divergence theorem, and so therefore I just put a minus sign there. Yeah. Yes?
So when you say the unit sphere, that's always a solid instead of...
No. So, sorry. The ball is always a solid. The word ball means solid. Think like, baseball. Right? Don't think basketball. Right? This is weird to do. But so solid is the ball, right? The boundary is the sphere. Yeah, that's the standard terminology. Yeah, right. Okay, so that does it for chapter 15. Yeah, right. So now you see what I was saying. A lot to digest, a lot to absorb. Now, by the way, let me further say, aren't you glad that we skipped the optimization temporarily so that so all this chapter 15 stuff, you're sort of, you had this past weekend, for example, to be digesting it now, right? In a lot of classes, Stokes' theorem and surface independence, they haven't gotten to that yet. That's going to come up on Friday. Right? So, and it's like, whoa, it's like last day of class, okay, Stokes' theorem, see you later. And then final exam. Right? So, anyway, I think it's very, very useful to give you all as much time as possible. Chapter 15's got so much to digest. There's so many different points of view, so many connections, so many relationships, symmetries, so much going on. And so y'all have got more time to digest that now. And now let's go back and finish up chapter 13. The good news about this chapter 13 stuff is it's just not as sophisticated as chapter 15, right? So, anyway, here we go. I've got 9 minutes to do a little bit of stuff, and we're going to get a surprisingly large amount of stuff done because this does go really, really quickly. Reminder about single variable optimization, right? So there's rules in the interior. You take the derivative, set it equal to 0. Look for points where the function fails to be differentiable. What are the rules for deciding on the boundary whether you need to check those boundary points? The answer is you always check the boundary points, right? But more specifically, there's different rules, right? So we treat boundary points differently than we do interior points. And the same thing happens in the multivariable case. Oh, excuse me. So here's a two-dimensional domain. You could imagine a question of, some function that's defined on this domain. Let's pretend we're studying economics, and this represents the set of possible choices in an economy or something, right? Certain constraints, and like this is interest rates, and this is inflation or something, and of all these possible choices of how we can choose to whatever. We want to maximize growth. I don't know, something like that, right? Profits, whatever. Well, you're trying to optimize a function defined on a domain. It's just that now the domain is two-dimensional, right? So what's the deal? And the first thing I want to point out is that, the first thing about the deal is that on the interior, there is a set of rules for finding what we're going to call critical points. Familiar, right? Certain rules. And then there is a separate discussion of what do we do with the boundary. And again, it's different rules, right? So what those rules are in the multivariable case is a little weirder for boundary. Look at the boundary's not just 2 points. In the single variable case, this boundary, you've got 2 points. You don't need some sophisticated rules to help you narrow down that list. It's just 2 points. Just check them. Right? Here, the boundary consists of infinitely many points. I can't just check them. I don't have that kind of time. Right? Infinitely many points. So we're going to have a game to, how do you deal with the boundary? That is, however, a separate story. Right now, we're going to focus on the interior. Wrong color. Anyway, we're going to focus on the interior, and here's how that works. A quick reminder about single variable calculus. I'm going to give you sort of a seemingly backwards point of view that I claim is really the right sort of forward. This is the direct point of view on single variable optimization, and that is, it's not a matter of, look for where the derivative is 0. Let's first focus on where the derivative is not 0. Where the function is differentiable, right, and the derivative is not 0. The reason we would care about these points is that means that in one direction or the other, the function's increasing. So, for example, here at this point, you go that way, the function is increasing. There's no way that point could possibly be a maximum. Right? Likewise, now at this point, now here the derivative is negative, right? The function's not increasing. Well, yeah, not if you're going to the right, but if you go to the left, the function is increasing. So one way or the other, the reason we care about these criteria, differentiability and whether the derivative is non-zero, is because that allows us to confidently, no question about it, eliminate candidates as possible maxes. And amazingly and powerfully, this applies almost everywhere in the domain, right? It applies, so for, okay, sadly not there, right, and not there. But I can eliminate all of these other points. Forget about it. No way could these possibly be maxes. Right? Now, sadly, again, I don't know about the boundary. That's a whole separate question. I don't know about points where the derivative is zero. But the vast majority of the points in the domain, gone. Yeah? So this is sort of the active part of optimization. And this is, in other words, this is the part that even though, this is kind of the part we don't care about, I suppose, right? Because we're looking for the maxes, not the not maxes. But the point is, this is something we can actually draw confident conclusions in. When you turn this around, you don't get, let's look at these points. If you say that didn't happen, either the function failed to be differentiable or the derivative failed to be non-zero, you don't get a conclusion that it is a maximum. What you get is, I don't know, my strategy failed. I don't know how to deal with this. I don't know. Right? So my point is, the confident conclusion, what you really know, is when you don't have a max. Right? If you take the derivative, if you apply your formulas, whatever your system is, and it fails, you know nothing. Okay, and of course y'all know. I mean, here's some pictures. Like here's a point. The function fails to be differentiable. Doesn't mean this is a max, right? It just means I don't know what's happening there based on this one simple-minded strategy. Okay. Likewise, here the derivative is zero. It failed to be non-zero. Does that mean it's definitely a max? No, of course not. Look at it. It's clearly not a max, right? So anyway. Got to keep that in mind. What we have is a ruling out process, not a sort of algorithmic derive, and whatever you get at the end of the algebra is definitely your answer. Okay. All right. It's the same in multivariable. Wonderfully analogous. Two-dimensional domain. Again, keep in mind we're starting off by considering points in the interior. Well, let's suppose at some point in the interior that the function is differentiable and the gradient is non-zero. Gradient, not derivative, gradient, which is kind of a derivative, right? But anyway, that's the multivariable version. Well, that means that the function is increasing in that direction. That means that could not possibly be a maximum, and I can eliminate that as a candidate of what I'm looking for. Yeah? Everybody on board? Okay. Again, it is a ruling out process. When this fails, function fails to be differentiable. The gradient fails to be non-zero. In other words, when the gradient is equal to zero. That doesn't mean really much at all. All it means is my process failed. It means it's really more of a commentary on us than it is on the function. Right? It means that our simple-minded process just didn't tell anything. So don't make the classic blunder, which is to think, look, a lot of students think, the way you find maxes is you take the gradient, you set it equal to zero, and you go through and you find those x's. And those have to be maxes or something, but they're not. Right? And easy examples to the contrary. Now, sometimes you do have a max. Sometimes you have a min. Easy, comparable picture. Right? But you could have a Pringle point, aka saddle point. Right? And it gets weirder. You could have what I like to call a shoulder point. Right? So there's kind of an inflection point in this direction, right? But there's it's like a max in that direction, but it's not a max in that. I mean, this is a weird thing. There is no single variable version of this, right? And then likewise, there's something called a monkey saddle. Right? And this is a good picture of it. So this this is a really weird function. It's not a shoulder, right? And so they put the monkey is for sort of visual aid, but you can see that the way this saddle is shaped, there's kind of a downslope for his left leg, and there's a little downslope for his right leg, and there's a downslope for his tail. Isn't that adorable? Right? So that's just this other shape. And here's a different picture of it, by the way. That one's a pretty, unobscured picture. You can see it's kind of like a Pringle, but that's a weird Pringle. You would show all your friends if you got this out of a tube of Pringles. Right? Okay. So fundamentally different. And there's all sorts of variations. I mean, that's a weird shaped saddle right there. I don't know what kind of animal uses that saddle. But, octopus saddle, spider saddle, something. Okay, so bunch of weird, I clicked on the wrong thing. A bunch of weird different possibilities. And the algebra is, it is what it is. So take the gradient, set it equal to 0. If you're looking at this function here, there's the gradient. Per the rules, set it equal to 0. I get these two critical points. Are these maxes? I don't think so. In fact, I know they're not maxes. Here, let's play the following game. Just plug in y equals 0 and then x equals 1 billion. Right? This function is way bigger than it is at either of these critical points. Right? So they're critical points. They're points that I don't understand. They're not necessarily maxes. Probably not. And in this case, also not mins. Plug in x equals -1 billion. Right? They're not maxes, they're not mins, they're some sort of weird, I don't even know what. Right there, yeah. Okay. All right. We don't need to talk about the stuff on this page, so I'm going to declare 263 is what we're done with today. And we're actually most of the way done with 13.5 at this point. A couple other little quick things I need to say. So we're going to finish up the course on Friday. Right? Don't forget, test on Wednesday, finishing up the course on Friday. See you then.